Swayam Prabha. Digital India. Educated India.
All right. So let's have a quick recall. Right. So what we did is we studied degrees, and we studied degree sequences, and we classified them as what we can call, or what the literature calls, graphic sequences, and we studied the Havel-Hakimi theorem. Okay. And the most important thing that you might have noticed is that we get a recursive algorithm to check if a given degree sequence, which is d1 greater than or equal to d2 all the way up to dn, is graphic. Right. So just as a warm up, let me ask you a intuition, right, intuitive question, and you can give me your intuitive answer. When is d1 greater than or equal to d2 the degree sequence of a tree? Do you have answers to this? So remember, we had a more complicated or rather more a general algorithm, right, which comes from the Havel-Hakimi theorem. So I give you a sequence of integer values in increasing order, n integer values, and I ask you, when is this the degree sequence of a tree? Right. So somebody actually mentioned that summation should be equal to 2 times n minus 1. Is this sufficient, or do you need something more? So for example, let me show you. Yeah, so let us not go there. This question is because it is for a tree, right? So let's identify, so one necessary condition is clear: the sum of the degrees must be 2 times n minus 1. Is this sufficient? No one should be 0 is correct, right? That's correct. But what more can you say? So if you think of it, you will come up with an additional condition. At least 2 values must be one, right? All right. So this is also necessary, right? Because any tree has at least 2 leaves, right? Okay. Is this still sufficient, or are there more necessary conditions? Okay. So interestingly, this is also sufficient. I will not give a proof here, but today evening when we meet, I will show you a very quick proof, or I will ask if somebody has discovered a proof, right? You can do a proof by induction, right, on the value of n. So therefore, it's also sufficient. Okay. So from a programming point of view, why would this be interesting? Why should anyone do this? I mean, we already had something which was more generic, right? So why should anyone ever come up with this condition? So here you have to think like a programmer and observe that there is no recursion here. It's a very simple check, linear scan of the given set of degree values, and one calculation of the summation, no other function call. Right? Therefore, this is a nice check. Right? So in terms of just efficiency or usage of the resources on your machine, right, if you just want a tree, right, then there is a significantly simpler algorithm to implement, where you don't have to implement the recursion which comes from the Havel-Hakimi theorem, right. So the key thing here is that no recursion in this implementation. So let's move on and talk about the other problem that we talked about yesterday, which is topological sorting. Let's go to the next page. So let's recall the topological sort without all the examples yesterday. The input is D, a directed acyclic graph, right. Output, right, is a linear ordering V1, V2 to Vn, the vertices of the DAG, such that if AB is a directed edge, of D, then A occurs before B in the output. So this is the condition that we want to place, right, and there are multiple applications here. Ranking, and if you are looking for a research problem and if you are looking for programming challenges, right, then here is the immediate programming challenge, right. Crawl right, you will go to the Association of Tennis Professionals, right, use your favorite programming language library, say Python or something, crawl the web page and pull out all the games that have been played in a year, right. The winner relationship of every match gives you a directed graph, fine. Now, of course, it may not be a directed it is most likely not a directed acyclic graph, because I mean there will be cycles there, right. So players will play each other, right, x will beat y, y will beat z, and z will beat x. So there are likely to be cycles there, right. So here is a research and a programming exercise, right. Rank the players by considering the as a diagram, right. Now I want you to tell me what kind of a ranking will you be happy with. So remember that you will have in your Association of Tennis Professionals data, x defeats y, z defeats a, and then a defeats x, right. So there are 4 factorial linear orderings, right? But the ones that you would want are the ones that maximize the number of edge relationships. That is, I would rather have a ranking where x is considered to be better than y, y is considered to be better than z, and z is considered to be better than a, right. But observe that a is going to be unhappy, a is going to come to you and protest, say that look, I have defeated x once, how can you put me at the last rank, right. Now the answer that you can give to this person is, look, this is the ranking that minimizes unhappiness, you are the only person who is unhappy. right, compared to other possible rankings, right. See, for example, Z might also come and tell you, look, I am very unhappy, I never played X, how can you rank me after X? Then you can tell Z that, look, X defeated Y and Y defeated Z, so you must be weaker than X, right. So what I am pointing out is that if cycles happen, then coming up with linear orderings, otherwise called rankings, right, is an interesting research problem, right, and you will have to come up with good justifications. This is not just associated with Association of Tennis Professionals, right. You can go and rank, for example, the shares of different companies based on their behavior, right. You can ask a set of stockbrokers in the market, look, among these two shares, which one would you prefer to own for this period of time, which one would you prefer to sell? Somebody says, I prefer this stock over this stock, then you consider that one stock has defeated the other stock. Based on such answers, you can create a directed graph and come up with a ranking of stocks in this example, right. So therefore, you can go around, look around the world, and wherever you see, right, this kind of a X better than Y local relationship, you can try to come up with a global ranking, right. So that's an interesting research problem. But what we will study, right, is a very simplified version of it, because we want to just analyze the asymptotic running time of algorithms. Right. So D is a DAG, right. Let's list the simplest algorithm. The first observation is that D has a vertex of in degree 0. Okay. I mean, this is something that I pointed out yesterday, and today Meghna also pointed this out. If every vertex has an in degree, then the graph must actually have a cycle, right. Therefore, it's a contradiction that it's a DAG. Therefore, there must be a vertex of in degree 0, right. So here is the algorithm. Iteratively in degree 0, remove printed vertex and update in degrees. Right? Fine. So how much time does this basically take? Let's just look at this. Right? Now you have to find the vertex of in degree 0. How can you do this? Right. So the immediate one is to keep an n-sized array and store all the in degrees, right? And you check if there is an in degree of vertex 0, right? So therefore, the straightforward algorithm takes, right, order, well, in the ith iteration, right, because you are removing the appropriate vertices, right. If you do it carefully, then it may take order I time, because there are only n minus I, sorry, in the ith iteration there will be n minus I vertices only, so it could take n minus I time, right. So in other words, this step is a very expensive step, just finding the vertex of in degree 0, right. Now you have to remove it, right. So if you maintain an array, right, and if you are going to remove this vertex of in degree 0, right, so then what should you do? Here is quite a complicated step. You have to somehow mark that this vertex should not be considered again, right. So let us say that we do this by putting a -1 there, right, and it must have had an out degree to other vertices, because you are going to remove this, you may want to reduce the reason I put a -1 is you can uniformly implement it by reducing the value in the matrix by -1 for other places. So subtract -1, subtract -1, subtract -1, subtract -1. Why are we doing this? This fellow has edges going to this vertex, this vertex, this vertex and this vertex. Because you are going to remove this vertex, all these edges will go. Therefore, you will subtract the in degrees of those vertices by 1. So therefore, this -1 is a natural thing to do when you remove, easy to implement, right? Therefore, you observe that the amount of work that is involved, right, per iteration is n, and just to update it is the sum of the out degrees. So So the second part is a very careful counting, right? Therefore, what does this give you as a complexity? It essentially gives you n square plus the total number of edges in the graph, asymptotically, right? So in every iteration you will have to do, in the ith iteration you may have to do n minus I amount of work to find out a vertex of in degree 0, right? And then when you remove a particular vertex, you will have to mark it as -1 and look at everything which is going out, right, and reduce the in degrees at all those places, right. So when you remove an edge, you will remove an edge only once. Therefore, the total number of times you will remove the edges is, right, remove edges is only the total number of edges, fine, right. So it's n square plus n, right. Okay, are there ideas to make it better? See, it is not just the subtraction that is, you have to go check that value, no? So therefore, this step, right, so this and this, even if you don't subtract, that work is there. So you cannot, just by not subtracting, you don't gain anything. Yes, right, okay. So this I will leave it as a small exercise for you to come up with a clever data structure where the minimum is always accessible quickly. So in other words, you can still, by using a careful data structure called a priority queue. So what does a priority queue do? It maintains a set of values, right, and it ensures that you can access the highest priority element immediately, which means in constant time, right. And such a data structure is called a priority queue. It is implemented on top of a data structure called a min heap. So that I am not going to present now, but by just hacking this idea, by choosing a better data structure, the better data structure is somehow to ensure that if a value becomes 0, it has to come to a place where I can access it quickly and update the data structure in efficiently, right. So therefore, using data structures like min heap, right, or a priority queue, you can cut it down to n log n plus m, fine. That is, pulling out the vertex with least in degree, right, can be done very quickly, right, and updating the in degrees of other vertices, this can be done fast, fine. Okay. Let's try to use DFS now to do even better. The reason I am showing you this whole sequence of thought processes is that DFS basically is fundamentally different from maintaining this nice data structure.